Hello, and welcome to this Gresham lecture on understanding the universe with AI. Artificial intelligence is today everywhere in our lives, and perhaps it might come as no surprise that it's playing a role, an increasingly important role, in our understanding of the universe and the way we investigate the cosmos all around us. In fact, today we will see that artificial intelligence will be absolutely crucial to make the next step in understanding where the universe comes from and what it's made of. Equally important, research in cosmology and astrophysics, which is often seen as disconnected from real-life concerns, is actually producing very relevant insights into the workings and features of AI itself. So we will see that these two apparently very disconnected realms of scientific and technological endeavor are actually going forward hand in hand. Our story begins on the 20th of February 1947, when a relatively young man with boyish looks walked into the grand courtyard of the Royal Academy in Piccadilly in central London. It was a bitterly cold February, and ice fields, ice blocks had been reported off the coast of England that day. So we can imagine that man going into the courtyard of the Royal Academy heavily wrapped up in a scarf and hat, perhaps to protect against the cold. That man was none other than Dr. Alan Turing, the famous mathematician who would, in time, come to be considered the father of AI. Alan Turing went to Piccadilly to deliver a lecture to the London Mathematical Society, a lecture that became duly famous because in it he foreshadowed essentially what we now call artificial intelligence, although the name had not been used by him at the time. It was coined only later in the 50s. But like many other ideas of Turing's, he was well ahead of his times when he posited in his lecture that the eventual aim of research into computing machines was to deliver a machine that can learn from experience. Turing's notion was to go way beyond what early computing machines were capable of in his time, namely to deliver a new way of programming computers so that computers could depart from the programming instructions that they were given if good reason arose. So he foreshadowed the idea of creating computers that would learn from experience, that would learn to execute commands and programs not just from the input given to them by the programmers, but rather from experience itself, and they would learn how to adapt to new circumstances if given enough examples to learn from. This was an idea that was way ahead of the times. We can only recall that at the time when Turing exposed his ideas about machines that can learn, the computer era, the modern computer era, hadn't even begun. In fact, the computers at the time looked like this, a room full of valves and instruments that look rather primitive to us today. They were fed by punched cards by human computers, mostly women who would translate written instructions into punch cards to be fed into the computers. And the computers had memories that were driven by tubes filled with liquid mercury, for example. So really very primitive machines with respect to what we are used to today. But Alan Turing, in his visionary genius, had foreshadowed what we now call artificial intelligence, namely a branch of computer science that develops ways for computers to learn from experience. Around the same time, actually 20 years earlier or so, we can also trace back the birth of modern physical cosmology. And perhaps if there is a birth date of physical cosmology as we know it today, that date is probably October the 6th, 1923. This is the time when Edwin Hubble, an astronomer at Mount Wilson Observatory in Pasadena, California, made a momentous discovery. He had been looking at distant nebulae, that's to say, extragalactic objects, galaxies outside our own galaxy, and in particular, he had been scrutinizing the closest galaxy to us, the Andromeda Galaxy, which we today know is 2.5 million light years away from us. At that time, nobody knew that there were other galaxies in the universe except for the Milky Way, and in fact the debate was very much about what is the size of the universe, what are those fuzzy objects in the sky that telescopes at the time could barely resolve. Are they objects in our own galaxy? Are they galaxies in their own right? How big is the universe was the fundamental question of the times. Hubble was building on the work of Henrietta Swan-Leavitt, who was a pioneer astronomer in her own right, whose contribution to extragalactic astronomy was fundamental. Because what Henrietta discovered a few years earlier in 1912 was that if you look carefully at a category of stars called Cepheid variables, those stars were known to change their luminosity over time, to be periodic variable stars. So they would brighten up over time and then dim again and then brighten up again in a regular pulsation of light. She discovered in 1912, by looking very carefully at about 1800 variable stars of that kind, that a certain category of those variable stars had a period of luminosity of brightening and dimming that was closely related to their brightness, to their average brightness. Therefore, if you measure the period of those Cepheid variables, you could work out their intrinsic brightness, how bright they were, and from that, using the equivalent of the inverse square law, you could work out the distance to those stars. So she invented a new method of measuring distances far away in the cosmos, something that had baffled astronomers for a long time. It is very, very hard in cosmology to work out how distant something is from us, simply because if something appears dim to you, you don't know whether the dimness is due to the distance and the object is intrinsically quite bright, or whether the object is intrinsically dim and close by. So working out distances was a crucial step to determining the size of the universe, and in particular to working out whether Andromeda, the Andromeda Nebula, was a galaxy far away from us, or rather a cloud of gas quite close by. So Edwin Hubble in 1922 started his ambitious program of observing, scrutinizing the Andromeda Nebula night after night. And on October the 6th, 1923, he finally got what he was looking for. And you can see here in the picture, in the central panel, the original picture taken by Hubble of the Andromeda Galaxy. It's a negative picture, so light shows up as dark in this picture. And you can see in the red square a little crosshair line marked by Hubble himself with the annotation var, with an exclamation mark. And var stood for variable. This was one of those variable stars that Leavitt had previously identified as being good distance indicators. And on the right-hand side, you can see the trace plot that Hubble made of the variability of the luminosity of that star, which in turn, given the period of 31 days, gave him access to a measure of the distance of that star, and therefore a distance to the galaxy it was in, Andromeda. Hubble worked out that Andromeda was about 1 million light years away from us, which is 2.5 times too small than the value accepted today, but nevertheless much bigger than anything else that could be part of our galaxy. And therefore, it worked out that the Andromeda galaxy was a galaxy in its own right, and all of a sudden the universe exploded in size, and Hubble essentially gave birth to physical cosmology as we know it today. Hubble was not finished, however, with his discoveries, and he built on this success in 1923 by continuing an ambitious program of observation, building on the work of Slipher before him, and also on the theoretical insights of the Belgian priest Georges Lemaitre, who is pictured here at the center of this photograph taken around 1933. The man on the right-hand side of this picture, of course, doesn't need any introduction. The man on the left is Millikan, the discoverer of the origin of cosmic rays. So Georges Lemaitre was a theoretician. He was a very gifted mathematician who used Einstein's equations of general relativity to work out that the universe was expanding. And so, in a sense, he foreshadowed the expansion of the universe as discovered by Hubble and then later also accepted by Einstein in the 30s. A true pioneer of cosmology. Hubble, on the observational side, carried on his careful measurements of distances of galaxies by using the same method by which he had measured the distance to Andromeda. And what he discovered was that there was a clear relationship between how distant a galaxy was, you can see that on the horizontal axis in the picture, and the velocity at which it moved away from us on the vertical axis. He first of all discovered that most of the galaxies were actually moving away from us. So not all galaxies were moving randomly, rather the contrary, most galaxies were moving away from us. And as you can see from the picture, more distant galaxies were moving faster than close by galaxies. So this could only be explained and understood in terms of the general relativistic model of Einstein, namely the idea that the universe itself was expanding and growing over time. And as it did so, distant objects were being expanded away from us faster than close by galaxies because of the larger amount of intervening, expanding space between us and the distant galaxies. So this relationship between distance and recession velocity, the slope of the line that you see in the graph, is to this date called the Hubble-Lemaitre law. It was called the Hubble law for a long time until 2018, when the International Astronomical Union voted by a wide margin to recall it, to rechristen it Hubble-Lemaitre law in honor of the important contributions of Georges Lemaitre to this field. And the slope of the line that gives the expansion speed of the universe today is called the Hubble-Lemaitre constant. Now, if you take the expansion speed of the universe today and you posit then that it is expanding over time, and therefore it was smaller in the past, it turns out that you can essentially wind back in your mind's eye the expansion of the universe, and the inverse of the expansion speed today gives you an estimate of the age of the universe. The amount of time elapsed since the universe, or rather the visible universe, was all compressed into a point. Now, Lemaitre and Hubble used their estimates of the expansion speed to work out the age of the universe, and it turns out that their number was way too low. It was about 2 billion years, which is smaller than the age of the Earth, which, however, at the time wasn't very carefully known, but certainly too small. So a universe that's 2 billion years, it's a young universe. It's not old enough to contain stars and planets like ours. So clearly something was wrong in the estimate of Hubble in terms of the expansion speed of the universe. In fact, today we've corrected this estimate by using observations that are much more refined and more abundant than Hubble ever had. We'll see this in a minute. And we now know that the age of the universe is of the order of 14 billion years. So much bigger than what Hubble and Lemaitre had originally estimated. But nevertheless, this discovery made in 1929 of the expansion of the universe was another fundamental pillar in the birth of modern cosmology. And this about 20 years or so before anybody could build a calculator, and certainly before Alan Turing came up with his own ideas about artificial intelligence and machines that can learn from experience. But we will see in a moment how all of these very disparate fields, physical cosmology on the one hand and artificial intelligence and machine learning on the other, who for many years just went on parallel tracks, in the last 10 years or so are rapidly converging towards common goals and common methods and helping each other achieve their respective scientific goals. Fast forward to the 21st century, when cosmology and astrophysics are making progress thanks to space telescopes, ground observatories, and even underground facilities, for example, buried in the Antarctic ice cap, and are relying on machine learning and artificial intelligence to not only clean the data, but also interpret the data and analyze the data thanks to high performance computing and big computer power in order to squeeze out from the data the information that we need to solve the big scientific questions of the day. And so we shall see that AI and machine learning is in a virtuous loop with astrophysics and cosmology, delivering research, education, and applications to real-life problems, both in terms of the methodology that AI provides to astrophysics and cosmology, but also vice versa. Astrophysics and cosmology given AI interesting, challenging, tough problems to work on, and therefore develop methodologies and algorithms that then can be used and applied to real-life situations in business and society. So really, the two fields today go very much hand in hand, and they develop in parallel, helping each other, as we shall see. There are many open questions in cosmology and astrophysics today, but I've selected 3 of the most important outstanding mysteries, which I think are fundamental to progressing our understanding of the cosmos. The first one is the nature and characteristics of dark matter. We now know that the universe is very, very strange in many ways. It contains only 5% of its energy matter content in the form of normal matter, and about 25% of dark matter, so 5 times more dark matter than normal matter, is present in the universe. Yet we do not understand fully what dark matter is made of. We have plenty of astrophysical, astronomical, cosmological evidence for the existence of dark matter. For example, here you see on the left a beautiful picture of the so-called bullet cluster, where you can see the color coding giving in purple and light pink the distribution of normal matter and gas in the cluster. Clearly 2 clusters which long time ago have met and have been colliding. So you see the bullet going through from the left to the right. This is of course of a timescale of hundreds of millions of years. While in blue, we see the map of where most of the mass in the 2 clusters resides. And you can see it's displaced with respect to the pink hue. And that's because most of the mass, which is also where the galaxies are in the 2 clusters, is actually represented or is actually in the form of dark matter. Matter that is not gas, otherwise it would show up in pink. Matter that is, we think, perhaps a new type of fundamental particle. So the nature of dark matter is very much one of the big open questions in cosmology. We know quite a lot about dark matter in the universe, but we still haven't pinpointed it down in terms of what it is actually made of. The second big question is what makes the cosmos accelerate? A Nobel Prize-worthy discovery made in 1998-1999 by 2 independent teams of astronomers was that the universe is actually not slowing down in its expansion, but it's rather accelerating, powered by some form of anti-gravity, which we call dark energy. Dark energy is now believed to make up 70% of the matter energy content of the universe, so the lion's share of the universe is in the form of something we truly do not understand in fundamental terms. The astronomers use a type of exploding star known as supernova type 1a, which is the small white star on the left in the central plot on the slide, to chart distances in the universe and thereby work out how fast the universe has been expanding in the last 6 billion years. And to everybody's amazement, they discover that the speed of expansion has actually been picking up in the last 6 billion years, an effect that is attributed to dark energy. That is one of the big open questions in cosmology today, and more data are needed to make progress. The third big question, which again has picked up enormous speed in the last 10 years or so, is the question of life elsewhere in the universe. We have discovered in the last 20 or so years thousands of planets going around other stars than the Sun, an incredible explosion brought about by technological advancement and a number of missions that have been able to spot those planets around other stars. Now the big question is, can we find life anywhere else in the universe, and what does that life look like? Whether it's simple life or advanced life, it really doesn't matter. Finding life elsewhere in the universe would change forever our perception of who we are in the cosmos? And so that's another big question. On all of these three fronts, progress can only be made thanks to new big data coming from various observatories in space and on the ground. And data are, in a sense, a mixed blessing for us, because yes, of course, more data mean being able to investigate further in more depth and with more precision the mysteries of dark matter, dark energy, and life elsewhere in the universe. But also, having more data means the necessity of having the capability of understanding this data and teasing out from them the kind of information that we are interested in, the scientific questions we want the answer to. So you see here how things have changed over time in terms of the amount of data that we have about the universe. The animation shows time elapsed since the 1800s and the number of objects in the universe as a function of their distance in the vertical scale and position in the sky in the two horizontal axes. The yellow dots are stars in our own galaxy, while the gray band are the asteroid belt in the solar system. At the top in green, you see galaxies, which begin to be discovered by Hubble, and then around 1990-2000, you will see a big explosion of data. An explosion of data which is brought about by digital technology, essentially, and the enhanced capabilities that it has given us to investigate the universe much faster in much greater detail than ever before. This is another example of the multiplication of data that we now have to contend with, in a sense. This is a modern-day equivalent of Hubble's plot that we saw a little while ago, but now extended to much more distant objects thanks to the Type 1a supernova stellar explosions that I mentioned earlier. And Hubble's work is now confined to the bottom left corner of this plot. We've been able to extend our capability of investigating the expansion history of the universe to much bigger distances and therefore much further into the past. Indeed, the kind of stellar explosions that we use for this work are also growing in number in terms of the capability of detecting them over time, exponentially so. You can see, especially after the 1990s, a true explosion, a real explosion of the numbers of supernovae discovered. Again, a feature of our increased technological capabilities. These data are only set to further increase by orders of magnitude with the Rubin Observatory, a mighty facility which is due to see first light in 2021-22, and which will produce 200,000 images of the sky per year, which no human eye can ever hope to be able to inspect, and which will need machine learning and artificial intelligence methods to be understood, processed, and used for scientific goals. The number of exoplanets is also growing very fast. This is a plot showing the number of exoplanets candidate by the Kepler telescope from a few years back. You can see there are thousands of dots in this diagram. The Earth, or an Earth-like exoplanet, would lie at the intersection of the blue lines at the crosshair. There is a great deal of candidates in the lower left corner. Those are planets that are smaller than the Earth and closer to their host star than we are. And in the upper right corner, that's planets rather like Jupiter, far away, big giant planets far away from their star. And there isn't all that many candidates in the Earth-like conditions place, and that's because we don't quite have the technological capability of seeing them yet. But in the future, things will change, and at that point, the hunt will go on for finding life in these Earth-like planets that we will no doubt discover in great numbers in the near future. In fact, we now know that there are probably more planets than stars in the Milky Way, given that about every second star hosts a planetary system, we now reckon, and planetary systems have multiple planets in them. And therefore, there are north of hundreds of billions of planets to be discovered in the Milky Way alone. So again, a great deal of information awaits to be discovered and awaits to be understood. Another important frontier in dark matter research, for example, is our capability of simulating in supercomputers the evolution of the universe from first principles. You see here one of such simulations, the Illustris TNG simulation showing the evolution of cosmic gas over the timescale of 500 million years after the Big Bang to today. You can see this mesmerizing cosmic ballet where all the gas dances under the influence of gravity, forming galaxies and clusters and filaments. And we can do this in very high resolution with very high detail, but we can only do it in a small number of cases because of the enormous amount of computing time that this kind of detailed simulations require. We would like to be able to do many such simulations to investigate different physical conditions for the universe. And that's another area where AI can help by giving us the means of producing almost identical looking simulations in a fraction of the time than it would take to do the real simulation. So this is one of the reasons why the era of big data, if you like, which was a buzzword 10 years ago or so, which is shown in blue in this diagram of interest in search terms in Google Trends, has sort of peaked a few years back. Big data is great, but big data is not enough. What we need is an intelligent interpretation of this big data, and that's where machine learning comes in, the orange curve that's picking up speed and picking up interest, indeed very much the technique of the day. So what is machine learning? Machine learning is a branch of AI, of artificial intelligence, and we might not know exactly what machine learning is or what it does, but we are sure to recognize it when we see it. And sure enough, it's everywhere around us today. Machine learning is behind recommender systems of the kind that give you suggestions for movies to watch online or your next purchase in online stores. Machine learning is the technology that is going to perhaps drive driverless cars in the future by recognizing images and situations that are quite different from anything that they've seen before, but the machine learning algorithm is capable of taking the experience that it has accumulated and learn from it to apply it in different situations, just like Turing envisaged so long ago. Machine learning is being used in medicine, for example, to improve diagnostic tests to levels that are it is now argued better than expert doctors. So, for example, diagnosing forms of cancers from various kinds of scans and images to a high level of precision and accuracy. Machine learning is beyond speech recognition, the kind of technology that powers the virtual assistants that we have come to know in recent years. But machine learning has got other applications too, sort of the dark side of machine learning, which could bring about mass surveillance, for example, by processing facial images of people in the street and cross-correlating big data sets in order to find out what people are up to and sometimes even foresee likely behaviors of people based on their credit score records, their whereabouts, their telephone calls, and so on. So really the potential for changing fundamentally democratic societies, and perhaps not for the best. Machine learning has got also military applications, and there is a great worry about autonomous lethal weapons. Those are machine learning powered combat systems that will be able to fire on enemies without any human supervision, again bringing in important ethical and moral dilemmas. So machine learning has got many facets, great potentiality for helping us craft a better future for humanity, but equally the potentiality for being misused in multiple ways, something that really concerns us all, and therefore something that is really an aspect of the present and the future that we should all have a say about. So let me give you a crash course in machine learning in a nutshell. Now I'm going to focus on a specific type of machine learning here to give you the gist of it. There are many different types that I'm not going to touch upon. But one popular version of machine learning that sort of encapsulates Turing's notion of learning from experience works like this. Imagine having wanted to build a machine learning system that is able to recognize the picture of animals, for example. You can imagine then widening this to all sorts of other pictures and situations you might care about. So the way to set up such a machine learning system is to feed it with a large number of samples of animals. So you build up what is called a training set. So you get pictures of cats, dogs, lions, penguins, and so on and so forth, each one of them with a label saying this is a cat, this is a dog, this is a lion, this is a penguin. You need big data to do this. You need a large amount of training images that you then feed into your machine learning network and let the machine adapt itself to learn from the features that it extracts from the images, and it will, over time, learn to distinguish cats from dogs and lions and penguins and so on. So the key insight is that you don't teach the machine that cats have furry ears and a cute face, while penguins are black and white and they have a beak and so on. You don't give this feature yourself to the machine learning system. The system learns the features that distinguish cats from dogs, from lions, from penguins by itself. It learns from the experience that you feed it in terms of the training data set. And so then, when you present the machine with a new instance of a picture of an animal, like the puppy that we see here, and you don't know what that is, you don't have a label attached to it, the machine learning system ought to be able to interrogate its knowledge as acquired from the training set and give you the answer that this is a dog with a certain degree of probability if the machine learning is a probabilistic system. So really we see this at work in all the kind of examples that I showed you before. And what it does, it encapsulates what Turing envisaged in another famous paper in 1950, when he said, why not try to produce a program which simulates the child's mind? That's the machine learning system before it's trained. If these were then subjected, said Turing, to an appropriate course of education, that's the training process that I described, one would then obtain the adult brain. So this kind of idea is what is at the base of the machine learning systems, or many of the machine learning systems we see deployed now in many sectors of society. But in particular, for our scientific needs, what we might want to use these systems for is as follows. Here's an example showing a machine learning system that has been fed a number of faces of real people. Those are the two strips of people on the left and on the top. And then the machine learning system has learned what makes a face, and it has now learned to generate new faces on its own by mixing the faces of people it has seen. So it has become a generative system, a system that has learned from experience to generate new faces of people that have never existed, and yet they look realistic. They look as if they could exist. We can use the same kind of technology to shortcut expensive dark matter simulations in the universe. So here you have an example where you see little squares showing snapshots of a dark matter simulation of how dark matter evolves with time in the universe. It's a kind of simulation that takes a lot of computer power, a lot of effort, a lot of time to put together. We can't do too many of them. But if we can train a machine learning system to learn what makes a dark matter simulation look like a dark matter simulation, rather like the faces, then we can get the machine learning system to produce an almost instantaneous guess or an interpolation of what dark matter will look like, which is on the right-hand side of this diagram. And you can see that while they do not look exactly the same, they are statistically very close, and therefore we can use machine learning system to speed up our dark matter simulations and therefore speed up the pace and the power of cosmological research manifolds. Another example of applications of machine learning in astronomy is to be able to look at the large number of galaxies that facilities such as the Vera Rubin telescope will produce and classify them for us according to their shape, which is one of the basic properties of galaxies. And it is one that we need to understand in order to, for example, understand the role of dark matter in producing those galaxies. So you see here on the left a number of galaxies that the machine learning system has been able to sort autonomously without human input in different shapes. So for example, the green highlighted shapes are all edge-on galaxies, while the shapes in yellow are all spherical galaxies. And therefore, the machine learning system has learned by itself that it can sort galaxies according to their shape and characteristics, which then is useful for humans to further process the galaxies for our scientific purposes. The machine learning system has also learned to produce synthetic galaxies that look realistic. On the right-hand side, you can see strips of galaxies generated according to the groups on the left, and again, they look pretty much like real galaxies will look on the sky. So again, you can produce more galaxies, synthetic, fake galaxies, for testing and training purposes of our algorithms. Another place where machine learning might come to the rescue or will be needed to help us is to clean images of the sky from unwanted disturbances and foregrounds. Unfortunately, we're now facing a crisis in astronomy in terms of our ability to see a clean sky from the ground, not just and not only because of light pollution. Of course, light pollution is a big problem for astronomy, even for amateur astronomers, but a problem that can be resolved by building big telescopes on the top of mountains in remote locations. We now have another problem, which is the exponential increase in the number of low Earth satellites that is being brought about, this new rush to space. Many private companies now planning or already deploying thousands of satellites which are designed to bathe Earth in a global web of internet connection, broadband. This is a big problem for astronomy and also a big problem for preserving the sky as our common heritage, as many of these satellites are also visible by the naked eye. But once the sky is covered by thousands of crisscrossing satellites, clearly every picture we take of the sky from our telescopes will be ruined in great part by the trail that these passing satellites leave. This is an example taken recently from the Blanco telescope, and this exposure of the sky. You see 19 diagonal traces left by passing satellites. This is set to become much worse in the near future. And so our efforts of seeing the sky are now being hampered by those satellites that are really becoming a big problem for astronomers. And machine learning might be able to clean away some of those trails and give us access to a cleaner sky. But some of them are just irrecoverable. The data are just corrupted, and we will lose our capability of seeing a clean sky for good if this deployment goes ahead as planned. But machine learning is not without challenges. I've now outlined a couple of ways in which machine learning can help astronomy and cosmology deliver our science in the future of big data. But machine learning has got its own problem, its own shortcomings. One of them is the so-called bias problem. The fact that machine learning can be very confident in, for example, assessing the type of animals it is seeing if the new animal we presented with is of a type that it has seen before, it has been trained on. But what happens if we now present to our machine learning system a new animal, say a fish, that the machine learning has never seen before, or a type of animal that it has only seen a few examples of? At this point, the system will be falling back on its pre-acquired knowledge, and therefore it will give us an answer among the categories that it knows about. So in this example, if we present our trained machine learning with a picture of a fish, it might say that it's a lion. And it might say so with high confidence, completely wrongly, of course, because it has never seen a fish before, and so it would not be able to recognize that it's making a mistake. So this is a big problem for machine learning systems, because they can be deployed in situations that they've not been trained on, or where their training is insufficient, and we don't have a good means of assessing when this is the case. And this matters a great deal, not just in astronomy, but it matters a great deal in society. So we've seen examples a few years back, for example, of pictures of black people being misclassified as gorillas by machine learning systems, because obviously the training set of these machine learning systems did not include sufficient number of pictures of black people. So a strong diversity bias problem, a problem that has still not been solved by these companies. We've seen more recently in 2019 papers highlighting the danger of facial recognition being inaccurate, especially for dark-skinned people, more so for female dark-skinned people. And so if we see now technology that's being deployed in real life that relies on facial recognition, if that technology is unreliable for a certain category of people in certain ethnic backgrounds and gender, this is a huge problem for the applications of this technology. There's also evidence that intelligent systems learn about, if they learn to converse, learn to interpret text or even voice based on existing databases of text or vocal commands, they will also pick up gender stereotypes that are ingrained in those text and voice collections. Therefore, far from becoming a more equal society because decisions and choices are left to algorithms, those very same algorithms will pick up and multiply manifolds our own existing gender and ethnic stereotypes and biases. And that is something that is very dangerous because it gives the veneer of objectivity of a machine learning system, which in reality is as biased or even more biased than we ever were as humans. So this is a problem in many ways in society. Is a problem for medical applications of AI, where, for example, dark-skinned patients do not have access to the same accuracy of detection of cancers, let's say, or of skin cancers than fair-skinned people because of this bias training problem that I've described. And that's where cosmology can come in and help machine learning develop solutions to these kind of bias problems. In fact, when we look at explosions of supernova type 1a stars in the universe, we also suffer from a similar type of bias as these machine learning systems because our training sets are not necessarily fair. In cosmology, we don't have access to unbiased training sets. So methodologically speaking, the kind of biases that we see in cosmology are of the same kind as the kind of biases that can lead to these very deleterious outcomes for society. So the suggestion is that we can actually use cosmology as a test ground for AI, as a challenging sandpit in which we can develop algorithms, ideas, solutions to these problems that are then applied to cosmology and astrophysics, to the big questions that we face there, and then hopefully once they have been validated and understood, can be developed and applied for societal problems as well, with the much bigger consequences in terms of fairness and societal bias that we discussed. So we see here the full circle coming together, namely AI providing useful tools, indispensable tools for cosmology and astrophysics. On the other hand, the study of the universe giving us a test ground and fascinating, important problems on which to test the AI systems of the future and make sure that they deliver for everybody in society and not just for a subset of people. So in conclusion, we can definitely say that the future in cosmology will heavily rely on AI and machine learning because of the big data challenges that we are facing coming from space, from the ground, from underground. All of these data sets will need AI and machine learning to be understood and to be really useful for delivering the answers to the big questions that we are facing in the study of the universe today. What is dark matter made of? What is dark energy made of? Is there life elsewhere in the universe? We will not be able to answer any of those questions unless we develop machine learning and AI algorithms that will help us. On the other hand, machine learning and AI are very, very important to society today. They have multiple shortcomings still, and working on those by using the example and the exemplar of algorithms and solutions developed in cosmology and astrophysics will make sure that machine learning and AI give us access to a better society for everyone, and not, we hope, to a dystopic future where only the few can reap the rewards of this very powerful technology. Thank you very much.